Hello everyone, I'm glad to present the research titled EAGLEYE, Exposing Hidden Web Interfaces in IoT Devices via Routing Analysis. The author cannot be on-site because of the visa issue, so I'm here to present their work. The exponentially increasing use of IoT devices also comes with growing threats. As reported, the number of vulnerabilities and attacks against IoT devices has grown significantly in recent years. Among various security issues of IoT devices, the hidden web interface is often overlooked due to their hidden nature, but it leaves undisclosed access channels to attackers and is very likely to cause serious incidents. However, the definition of such threats is vague. Fewer solutions give clear definitions. What are hidden web interfaces in IoT devices? The paper defines an interface as a gateway for clients to access specific functionalities or services of a device, establishing the rules for client-device interaction. For optimal user experience, all interfaces should be accessible through a centralized partition with clear documentation in the user manual. However, hidden interfaces, which are undocumented and untraceable, are the focus of this paper. The firmware managed interfaces through handlers. A routing mechanism parses interface requests and directs data to the correct handlers based on routing tokens in the request. These tokens, each corresponding to a specific interface, form a routing table that defines the routing rules. The figure illustrates how routing tokens get requests to the appropriate handlers. So, how to find hidden web interfaces in the IoT devices? Discovering hidden web interfaces is challenging for traditional bug-finding solutions because there is no clear pattern for static analysis, and triggering hidden interfaces provides no obvious feedback for dynamic testing. For example, fuzzing cannot target unknown interfaces, and taint analysis struggles to define sources or sinks related to hidden interfaces. The routing mechanism is closely related to routing tokens in request. We can focus on code selects involving routing tokens, as most tokens share a consistent pattern in their context, as shown in the figure with 3 real-world examples. As the routing token links the input test case and the interface, they firstly identify routing tokens from public requests. Then, they extract context among public routing tokens in programs, learning and deducing their common pattern. Next, with the learn pattern, they try to extract more similar ones and obtain the maximum approximate set of the routing table. Finally, with the help of the routing table as a dictionary, they perform a directed black box fuzzing to mutate the field of the routing token. Black box fuzzing is convenient and avoids the dependency on heavy instrumentation and rehosting. Their solution, EAGLEYE, was developed based on this intuition. The solution comprises 2 stages: intelligent routing analysis and directed black box fuzzing. In the first stage, routing analysis extracts the routing table from the firmware, leveraging the LLM's pattern learning capabilities. In the second stage, they perform directed black box fuzzing to expose hidden interfaces. They decompose requests into tokens based on their grammatical structure and compare tokens with the same fields to identify variable tokens as potential routing tokens. However, certain token types can interfere with routing token identification due to their variability. They eliminate this by leveraging their temporal characteristics. For multi-level tokens, they cluster requests by routing tokens. If multiple requests share the same token, they establish a partition order between the upper and lower routing tokens to handle hierarchical dependencies. Either public interfaces or hidden interfaces in one device are generally dispatched in the same way. Therefore, the context of routing tokens, including public and hidden ones, generally share a similar code pattern. They leverage LLM to learn the common pattern among public routing tokens contexts. Then they use the learned pattern to analyze web programs and try to find the hidden ones. They develop two tailored prompts for the LLM to analyze extracted context. First, the LLM analyzes code surrounding routing tokens to understand program semantics and extract tokens, considering their potential concealment with control or data flow. Second, to address challenges in comprehensive routing table extraction and reduce false negatives, the LLM learns formatting patterns of routing tokens and generates regular expressions to scan programs for similar tokens. If a file is used as a routing token, the local file system directory tree is included in the search space. To guide the LLM to learn the correct patterns and mitigate initial errors, a self-correction model is designed for iterative adjustments. This model uses both positive and negative samples to assist error correction during the prompt process. A subset of public routing token is allocated for verification, where the remainder forms the corpus for the LLM to enhance its understanding. EAGLEYE evaluates each LLM output against the verification site to identify missed and correct instance. Through finite iterations, the LLM can progressively refine its understanding and master the pattern. They use public requests as templates and the routing table as a fuzzing directory to generate high-quality seeds for EAGLEYE to explore different interfaces. During fuzzing, they collect parameters from responses to create new requests. In black box testing, the device's response is crucial for determining the validity of the mutated request, indicating a potential hidden interface. They analyze invalid responses, which typically follow a general pattern despite minor variations due to reasons like unauthenticated or unauthorized access or incorrect parameters. These responses often contain unique string snips. They decompose responses into discrete snips and identify those exclusive to invalid responses to distinguish them. They have conducted a comprehensive evaluation of the prototype and will present the findings of the outcome of the evaluation analysis. They tested 13 commercial devices from leading manufacturers like Cisco, covering various types. Detailed information is shown in the table. EAGLEYE identified 79 hidden interfaces across the tested devices, with 27 bypassing authentication and 52 accessible after authentication. Over 19% of the devices has hidden interfaces, and over 60% has unauthenticated interfaces. Hidden interfaces after authentication were more common, approximately twice the number of those bypassing authentication. They compared EAGLEYE with IoTScope, a state-of-the-art solution focusing on URL-based and unauthorized authenticated hidden interfaces. In the evaluation, IoTScope found only 3 hidden interfaces. And EAGLEYE identified an average of 4.5 variable token fields and filtered out 2.0 inferring token fields. EAGLEYE used LLM to learn the varying patterns of routing tokens across devices, achieving automation and leveraging LLM's pattern learning capabilities. The accuracy of the learned pattern improves with a limited number of corrections, often reaching the highest level with just 1 or 2 adjustments. And as the fuzzing progresses, the number of parameters in the pool increases. triggering more interfaces and generating more parameters. This growth trend, shown as the blue line in the figure, reflects the effectiveness of EAGLEYE's mutation strategy in continuously producing better seeds. To evaluate the security risk introduced by the hidden interfaces, they further try to discover vulnerabilities on them. They discovered a total of 29 unknown vulnerabilities. And they present 3 typical cases and for causes under the hidden interfaces. More detail could be found in paper. In summary, they explain the significant problem of hidden web interfaces in IoT devices and give us a series of clear definitions. And they propose a novel solution, EAGLEYE, which models the problem as exposing hidden interfaces and the searching process. They propose a novel approach, routing analysis, to intelligently learn the routing pattern among interfaces and direct black box fuzzing. They evaluated EAGLEYE on 13 commercial IoT devices and successfully exposed 79 hidden interfaces, on which 29 unknown vulnerabilities, including backdoor, were found, and 7 has been assigned with CVEs. And the above is my presentation. Thank you for listening. If you have more questions, you can connect the author directly. Thanks.